All right, so I'm going to do my best to show you how the thought process works of going through and how you can find that something is differentiable or continuous, or in other words, how to force it to be differentiable and continuous. So at this point, you should have a sketch of what you want your roller coaster to look like. And again, it might change throughout depending on what functions work and what functions don't work, and if it's too difficult to find how to make it continuous or differentiable. So I have a rough sketch here of something you might have. So notice that I have this piece over here that's a constant function. It changes into something that's kind of curved and then kind of goes back to a straight line again, and then notice that it kind of comes back over here to a curved function again. So the constant function is pretty easy to create. So it's pretty easy to create that one first. We'll just get started. Honestly, you can make that any constant you want. So I know in my example I made it y equals 4, but we'll just make it whatever we want. So I liked to name my function, so we'll call this a of x. And the nice part about that was that you were able to, actually, it doesn't like vowels very much. So b of x, how about that? Oh, it still adds that in, but that's okay. It'll figure it out eventually. So we'll say b of x equals, and you can make any constant function you want. So I'm going to say b of x equals 3. And notice that it creates this entire line right there, and I don't want the entire thing, so I'm just going to limit the domain. So remember, in order to limit the domain, we insert these squiggly brackets. So if I insert a squiggly bracket and I'm going to say, I don't know, -3 is less than or equal to x, which is less than or equal to 0. So we'll say that's where my roller coaster is going to start. And notice that it restricts my domain just from -3 to 0, and that way I have my constant function. So we can call that our loading zone. So my goal is to create this roller coaster in between my two constant functions, and both of them should be at a height of 3 in this example, so that my loading zone and my unloading zone are the same height, so that people would be able to get on and off the roller coaster. So from here, if we go down and enter a new function, we'll call this new function c of x equals. So c of x, if we look back down at my sketch again, we did this constant part, and now I need to find some kind of an equation that's going to model this curved part. So if I was going to take a guess, there's lots of different functions you could choose for this, but I think the easiest one for me might be like a parabola or an exponential function or something like that. It could be even a sine curve or something, whatever you want to be creative with. I'm going to go with a parabola, and maybe the reason why is this. I know it needs to be continuous, which wouldn't be the hardest thing in the world to do. I could just move the parabola up or down to make it continuous. But in order to make it differentiable, it has to have the same slope as this constant function. And if you remember, the slope of a constant function will be 0. So I need to have somewhere on my function that has a slope of 0. And what I'm thinking, and I'll try to draw a sketch of this for you really quick. I'm thinking of a parabola, and it looks like that. And I know the slope of the tangent line is 0 right there at that turning point. So if I can kind of match that turning point up with this point right here, I'll know that they have the same derivative, so therefore it would be differentiable, and I can make it continuous by doing that. So essentially, I just need to enter a parabola that has a vertex at this point right here, so that I know that the slope at that point is 0, and it's also going to be continuous. So if we come back up here, the vertex here needs to be at 0, 3. So if I put my equation in vertex form, that would be a, I don't need an a value, so let's just say x minus 0, because there's no horizontal shift, so that's just x squared. There we go, x squared. And you guys can see my graph over here is starting to come into play. And then I'm just going to do plus 3, so that it starts off right there. Now, notice that I don't need this side of the graph, so I need to restrict the domain. I want it to start at 0, so I'll put in my little squiggly brackets. So if I put in a squiggly bracket, I'll start it at 0 is less than x, which is less than or equal to. And I always like that format. So the first one will have less than or equal to symbols for both of them. These ones after that will just have a less than symbol and then a less than or equal to. So that's usually the format that you see for piecewise functions. Is less than or equal to, and then you can kind of make it go as far as you want. So I could let it be less than or equal to 1, and it stops there. I could say it's less than or equal to 2, and then if I zoom out just a little bit, if you say less than or equal to 2, it goes a little further, so it kind of just depends on what you want your roller coaster to look like. So I'll keep mine less than or equal to 1, just so that it only keeps it limited to that first little part right there. I know that I would like to see the shape of the parabola in general, but again, this might be as good as I can get here. Maybe somewhere else, like if I look back down at my sketch again, maybe I'll be able to get a better shape of the parabola if I use a parabola for this function as well. So this might not be my best visual for the parabola's shape, but this up here should definitely help me out a little bit more. So this one's really just helping me to get started and to making that function continuous and differentiable. So here let's check to make sure it actually is continuous and differentiable. These are my two functions, so I'm going to write them down as piecewise functions. So here we go. Let's just say this function f of x equals, all right, and my first function was 3, when negative 3 is less than or equal to x, which is less than or equal to 0. And my second function was x squared plus 3, when 0 is less than x, which is less than or equal to 1. So in order to prove that it's continuous, if I plug 0 into both of these, I can show that it's continuous, because if I plug 0 into the top one, I get 3. If I plug 0 into the bottom function, I get 0 squared plus 3, which is also 3. So because they both equal each other in that case, I know it's continuous. In order to show that it's differentiable, I can take the derivative, so f prime of x equals, the derivative of 3 is 0, and the derivative of x squared plus 3 is 2x. And now, if I look to see whether or not it's differentiable at that point, I can plug in 0 again, which is my breaking point. If I plug in 0 to the top function, it's still 0. If I plug in 0 to the bottom function, still 0. So therefore, it is differentiable. This one's probably the easiest of all of them to make sure that it's actually differentiable and continuous, because starting off, you can automatically assume that this quadratic function should have the same slope as this function. So since it's a constant, it should be 0 at that point, and it continues from the turning point, because I know that the turning point of a quadratic function has a slope of 0. So that's kind of how I got it started. This next video is going to show you kind of how to take off from there. So let's do that one next.